Let's discuss system design from a different perspective, because I think there are a lot of YouTube videos which tackle the system design, but I just wanted to provide a different take so that value add to this video. Before we discuss, please like, share, subscribe, and hit the bell button for notifications. Also, I have added a lot of quizzes to the community page. Please check it out. Now, back to the system design. So, I just wanted to take the top 10 components used in system design and make a video on each one of them, so that you can you are aware of these are the 10 most common components as well. What are the individual things within these components which will help you in a system design interview. So the first one I want to deal with is the load balancer component. So they are very critical components in modern system architecture. They are designed to distribute incoming network and then or application traffic across multiple servers. Their primary goal is to ensure that the load is distributed evenly and no single server bears too much load. Thereby, that improves the responsiveness and of the system, as well as availability and reliability. So this is a simple application load balancer. There is like multiple load balancer types. We'll go through this video. So like the web clients doing over HTTP, HTTPS, and then there is load balancing, and then there is backend processing here. So the first one is the traffic distribution. They are supposed to distribute the incoming requests evenly across a pool of servers using various algorithms. And so the load balancers are need to check the health of the servers they are routing the uh, traffic to, and take them out if one of them is not functioning properly. So if there are like 10 servers and one of them goes down because of NIC card failure or something like that, then you route traffic only to the 9. And SSL termination is if they were able to load is able to decrypt the SSL coming over the internet, then it reduces the load on the application server, thereby improving the performance. And another thing is the session persistence, also known as sticky sessions. This basically ensures that the this same session will be routed to the same server number 5 or 1 or something like that. So that's so that it has that session data saved. You cannot, if you want session persistence, you cannot route the data to any server you want. You basically keep routing to the same server which handle the request from this session. So the load balancer types are like layer 4 and of the network layer, and then layer 7. Layer 4 is the transport layer. So here you're just looking at the IP addresses, and then based on that you basically route to whichever is the server which handles it. So this is usually faster but less flexible. It may not be uh, available, it may not be appropriate in certain situations, and especially in the case of sticky sessions, you cannot route to anything you want. So and the next one is the layer 7 load balancer. This is where you read the HTTP headers, and based on that, you make the routing decisions. So this is a little bit more complex and might introduce a little higher latency, because you need to read the packets, and based on that you need to decide where to route. So those are the trade-offs. uh, Now, coming to the some of the trade-offs with respect to load balancers, like the performance versus flexibility, as we discussed before in the previous two slides. Like layer 4 load balancers are faster because they are based on IP addresses, and layer 7 load balancers provide greater flexibility because of they are like higher application layer load balancing. And also the cost versus features, like simple round robin load balancers are very inexpensive and easy to implement, but lack advanced features like health checks, SSL termination, and intelligent routing. More advanced load balancers might offer these features, but they come at a higher cost. And also the centralized versus decentralized distribution. A centralized load balancer can become a single point of failure, whereas distributed load balancers offer more resilience, like DNS based or client side based load balancers, but they are very complex to manage. So these are the trade-offs. And regarding scalability, you can do horizontal scaling by if the load balance, you want to increase the current load balance. Basically you can add more servers to reduce to improve the performance basically. And then you can do vertical scaling, basically means you can add more memory, more resources, more CPUs to the existing servers, and then scale vertically that way. And also you can use cloud environments to do automatic scaling based on traffic patterns. So these are the scalability aspects of load balancers. And then regarding the redundancy and failover, you can have load balancers running in active mode. So where basically all the load balancers or distributing the load among them. And you can have active passive, where there is a primary load balancer and there is a shadow load balancer ready to pick up in case the primary fails. And then you can have DNS based load balancing for failover mechanisms, or you can do health checks and then do the failovers in that aspect. And also you can do something called a VRRP, virtual router redundancy protocol based setup to handle the failover scenarios. So in the case of availability, which is basically to do with the fault tolerance, by distributing traffic across multiple servers, you can make the whole load balancing system fault tolerant. And also you can do geographic distribution across multiple geographical areas, and then routing the users to the nearest data center. And also you can do health checks, ensure that only healthy servers receive traffic, reducing the chances of downtime due to server failures. And the common algorithms used in load balancers are like round robin, basically like you distribute the requests sequentially across servers. It is simple, but it doesn't account for the server load. Say for example, one type of API could take a lot of time, whereas the other API is very simple. So you don't consider you consider both of them equally, and it may not be efficient. And another algorithm is least connections. Basically you route to the server with the fewest active connections, so that way you can balance more effectively. And another algorithm is IP hash. Based on the IP, you hash it to a different existing server, and so whenever the traffic comes from that IP address, you route it to that same server. And another algorithm is weighted round robin. Based on the server's capacity, one server could be more have CPU cores, so based on that you do weighted round robin as well. And so some of the challenges uh, in the case of load balancing design is the SSL termination overhead, because they are doing the decryption of the SSL layer and sending out the non decrypted data to the application servers. It can add overhead and potentially create a bottleneck if not managed properly. And also the latency load balancing at application layer can introduce additional latency due to complex routing decisions based on the input headers, so you need to be aware of that. And then the session persistence, even though they are useful, they can lead to uneven load distribution, especially if one server becomes responsible for disappropriate number of sessions, so you should be aware of that. And in conclusion, load balancers are like essential components in ensuring the responsiveness and the availability of the system. They distribute the traffic efficiently, improve system resilience, and ensure high availability. However, the design and configuration of load balancers involve trade-offs that need to be considered carefully. And like you need to pick the right system for load balancing. Like some of the hardware providers are like Cisco, Juniper, and one of them is the Fi networks. Big IP as well is there. And the operating systems are like Linux is the most common one, I think, and then Unix is there a little bit, and Windows is also there, and then another important one is Fi networks, TMOS, I think, the system operating system. And so that's it. Let me know if you have any questions. Otherwise, I will see you in the next video.